Okay, the following is a video over 2.5 notes, and this is limits at infinity. And when I think of this, I think of limits as x approaches infinity or as x approaches negative infinity. So when x gets really, really, really big, what's happening to my y values? And as x gets really, really small, what happens to our y values? So what we need to do first is look at end behavior and know what that is. So I want to talk about that real quick. And we talk about the degree of our functions. So if the degree is even and the leading coefficient is positive, then we get a function whose end behavior goes up to the left, okay, and then up to the right, okay. And I think of the equation y equals x squared. Our degree is even, leading coefficient is positive, it's positive 1. And so the function looks like this, just the generic graph where you have the parabola going up to the left and up to the right, okay? Let's think of another scenario for end behavior. If our degree is even and our leading coefficient is negative, so leading coefficient is negative, then we go down to the left, so down left, and then down to the right, okay? And so I would think of the equation y equals negative x squared, and that is a parabola that opens down, okay? So down to the left, down to the right, all right? A third scenario is when we have our degree is odd, okay, and our leading coefficient is positive, all right? And so that would go down to the left and up to the right, okay? And I think of the equation y equals x cubed, okay, that function, and that function behaves like this, okay? So we go down to the left, up to the right. Okay, the fourth option that we've got is if our degree is odd and our leading coefficient is negative, okay, then we go up to the left and then down to the right. Okay, and so that I think of the equation y equals negative x cubed, and so and that function looks like this. Okay, so we go up to the left, down to the right. Okay, so that's just what's going on with end behavior, okay, just to make sure that you understand what's going on there. And I also want to talk about horizontal asymptotes, okay? And so we've got three scenarios for horizontal asymptotes. The first one is if the degree of a numerator is big divided by the degree of the denominator is small, then we get no horizontal asymptote, no horizontal asymptote, okay? Okay, if I take another scenario, let's say that the degree of my function in my numerator is small, divided by the degree of my numerator is the same. I'm sorry, not the same, is big. Okay, then we get that a horizontal asymptote is at the line, the horizontal line y equals 0. Okay, it's actually the x-axis. All right. The third option that we get is that the degree is the same in my numerator as it is in my denominator. Okay, and so now if it's the same, we get a horizontal asymptote, okay, that is defined, that is at y equals the ratio of leading coefficients. Okay, leading coefficients. All right, so let's just look at an example here real quick, and we've done this before. We've looked at this on the reviews. But if I write this out as an example, then let's just think of the function, say, f of x is equal to negative 3x plus 2 over 4x plus 1, okay? Now, the degree is 1 in my numerator. The degree is 1 in my denominator, meaning they're the same. So I have a horizontal asymptote at y equals the ratio of leading coefficients. So my horizontal asymptote on this function is at the line y equals negative 3/4. And so I look at my values here in front of my x's, my leading coefficients, and I take the ratio of those two numbers. Okay. Hopefully you've got some space to write that. There's not a ton of space, but hopefully we can make it work. Okay. So let's move on to problems 10, 20, and 24. And these are limits as x approaches infinity on number 10 of the function 5 plus 1 over x plus 10 over x squared. And so this one's kind of interesting because if I were to think about this function, okay, I've got 5, the function 5 plus 1 over x plus 10 over x squared. Okay, and as I plug in big values for x, okay, we're talking like 10 million, billion, okay, what's going to happen to these denominators? These denominators down here are going to get huge, okay, and as x gets really big, what happens to the y values? And those actually go to 0, okay, in both of these. So if you ever get a function with a number up top and then a variable down below, and you take the limit as x approaches infinity, they'll always go to 0. So when x gets really big on this function, you just get a value of 5, okay? All right. Now, let's take a look here on number 20. The limit as x approaches negative infinity, okay? What happens if I plug in values that are really small here, okay? Like negative 1 million, negative 10 billion, okay? What's going to happen here is that these numbers get really negative, even though you're adding plus x squared. I'm really looking at my leading coefficient, okay, or my degree and my leading coefficient, okay? So my degree is odd, okay, my leading coefficient is positive, so leading coefficient is positive. Okay, so I need to look at my end behavior here because I don't have a rational function. And so what happens as x goes to negative infinity, the y values, this limit value, also goes to negative infinity, okay? So it follows this thing, okay? My degree is odd, leading coefficient is positive. It's going to go down to the left. That's why I need to look at end behavior because it tells me what my limit is going to approach, okay? It's going to approach negative infinity. It's never going to stop, okay? On 24, we've got the limit as x approaches negative infinity. All right, well, let's first kind of rewrite this function. I'm going to rewrite this as the limit as x approaches negative infinity. If I've got 2 times x to the negative 8th power, that's the same thing as me writing 2 over x to the 8th, okay? And then plus 4x cubed. So if I plug in really small values like negative 1 million, negative 10 billion, okay, what's going to happen here? First of all, this is just going to go to 0. Okay, if my denominator gets really big, then the limit's just going to go to 0. So then what's going to happen is we go to negative infinity on 4x cubed. Okay, my degree is odd, my leading coefficient is positive, so this limit value is going to approach negative infinity. Okay, so guys, you know, the thing about some of these is that I'm not doing a ton of math. I just have to think about what these graphs are doing as x gets really big or really small. Okay, so now let's take a look at some rational functions here, and we need to look at the degrees of our numerators and denominators. So let's take a look here. We're asked to find the limit as x goes to infinity as x and as x goes to negative infinity. So if I take the limit as x approaches positive infinity here of this function f of x, Well, let's look at our degree. Okay, my degree is 2 up here, and my degree is 2 down here. So because my degrees are the same, I'm going to take the ratio of leading coefficients, okay? And that's just going to give me 1/2. Okay, 4 over 8 gives me 1/2. Okay. Now let's look at as the limit approaches negative infinity of our function f of x. Okay. So as we approach negative infinity, now what we have to consider here is what's happening to the sign here. Okay, because we are going to approach a number, because we have the same degree here and here, we have to make sure that as we approach negative infinity, that we're taking our sign into account. So what's going to happen here is that when I square something, it's always going to be positive, okay? So you do have to consider that a little bit, what's going to happen as x goes to negative infinity. And because my numerator stays positive and my denominator will stay positive, then what's going to happen is I'm still going to get the same limit value of 1/2, okay? So now, let's take a look at number 30. Now, the degree in my numerator is 4. The degree in my denominator is 5. So I'm going to have a horizontal asymptote at the line y equals 0. And so when I get that, if my y values will be negative if I approach negative infinity, or if they're going to be positive, as my values for x get infinitely large and infinitely small, they're both going to approach 0. Okay. So let me write that. So the limit as x approaches positive infinity of f of x in this scenario is going to be 0. And the same thing here, the limit as x approaches negative infinity of my function f of x is also going to be 0. Okay, so in this case, it kind of doesn't really matter when calculating your limits. If you have a horizontal asymptote at y equals 0, then both your limits will be 0. Okay, but 36 is where things change a little bit. Okay, now even though you see, this is kind of weird because we've got a square root and an x squared, what I notice here is that my degree of my function, let me change my color real quick. The degree of my function in my numerator is actually 1. Okay, my degree is 1 because if I take something squared and then I take the square root of that value that's been squared, I essentially have a degree of 1. Okay, now the degree down here is 1 as well. Okay, so it's the same. So my leading coefficient here was 1. And so even if I take the square root of 1, I'm still going to get 1. So I have a horizontal asymptote at the line y equals 1/2. Okay? So as my limit, as we plug in the limit as x approaches positive infinity of my function f of x in this scenario, we're going to get 1/2. Okay? But what we need to think about is what's going to happen to our limit as x approaches negative infinity of f of x. Now here's where it gets weird, okay? If I plug in really, really, really negative values into my numerator is always going to be positive. But what happens, folks, when I plug in really, really negative values into my denominator? Those are going to be negative. So as we approach as x approaches negative infinity, instead of just getting 1/2, we actually get negative 1/2 here, okay? So we do need to think about, okay, what happens when I plug those values in? Okay, what's going to be the result of that? All right, and so those are just some things to consider. But mainly, guys, if you know end behavior and you know your horizontal asymptotes and you know how to plug in numbers and determine the sign of that number, then you should be fine. Okay, let's take one quick look here at problem number 60, and we're given these different scenarios, and we got to draw the graph of this. Okay, so here's what happens. Okay, if I plug in -1 into my function, I get -2 as a result. That's a point. Okay, I'm going to plot that point here. All right, -1, -2. Okay, I also have the point f of 1 is equal to 2, so the point 1, 2, and then I have the point 0, 0 on that as well. Okay, and then as x approaches infinity, I have I get a value of 1. Okay, that means I have a horizontal asymptote at 1. All right, so I'm going to kind of draw that little asymptote in here. And then as I approach as x approaches negative infinity, we have a horizontal asymptote of -1. Okay, So what I want to do is I want to actually draw this function, okay? And I know that we have an asymptote at -1, so I'm going to do something like this, where it gets close to there, but then I want to make sure that we go through these points here, and then as x gets infinitely large, we approach that asymptote, okay? And we do that from the left and from the right. So you just want to make sure that your graph follows all of these, and that's about all I got. I hope you enjoyed this video. I know it's a little bit long, but please get started on your homework and let me know if you have any questions.